logs and things like that. And during this course, we also see, or we've also been learning that there's a growing trend of cybercrime and criminals in general to be using the internet as a communication medium for enabling, for facilitating their activities, okay? And oftentimes hiding behind anonymity systems to conceal their identities, okay? So this was one line of work. And at the other hand, I was also starting some research with other students in this branch right here, where the idea was to develop new techniques, machine learning techniques, to try to analyze traffic and try to circumvent censorship on the internet, okay? And so by just, thinking of these two things, these two lines of work, I start thinking, oh, what if we kind of come up with a framework or a system that could actually help law enforcement authorities to try to track down communications in the dark web, right? So this was how things came up, right? Because it's very useful. It's very useful for police authorities. It's very interesting from the research perspective because there's a lot of technical challenges involved in de-anonymizing these communications. And we thought it was an interesting project, okay? And so we started around in 2020, this seminal idea. We came up with this cool name, Torpedo, and we wanted to build a framework, a system whose goal was to de-anonymize Tor communications. And I'll explain in a second what are these Tor onion service sessions. And from this idea, we basically generated two proposals. Okay, so one of them was on the left-hand side, and we applied for a grant. This is a grant from CMU Portugal, and basically they give funding for sponsoring exploratory projects for 1 year. Okay, so we just built this grant around this idea. And at the same time, we started working right away on building a system. Okay, and we had a very, very strong master student. My PhD student was also involved. And so we made a submission to Usenix Security 21, so some years ago. What was the outcome? What do you think happened? Quite interesting. And I'd like to share this with you because sometimes we don't get to know these things. Okay, and I think it's kind of funny. And so the reaction was quite telling. Okay, on that end there, our reviewer said, oh, this is great. Okay, by just building such a system, you're going to make the world a better place. You're giving police authorities the mechanisms to track crime and all of that. So it's excellent. Okay. On the other hand, we say, no, this is awful. You're going to be building like tools for massive surveillance. This is horrible. Reject. So we had that paper rejected. Okay. And I'd like to share some of the comments that we've received. Okay. Some of them are going to be anonymized. And of course, I have an excerpt from our reviewer too, which, I mean, it's our usually friendly reviewer. And he said something like this. He said, my main issue with this paper is that it focuses on the technical side of law enforcement interventions and does not discuss the really hard part. How to ensure that the policies that rule the use of the system cannot harm any legitimate user of the Tor network. And then below it says the deployment of such a system can be extremely unsafe for all Tor users. Okay, and then below, so this was during the rebuttal, we tried to do our best to respond to all the concerns. There were also some technical concerns. Our system was still very slow, etc. But then in the post-rebuttal comments, we have something like this, saying that ultimately the problem was that the community was concerned that such a system can have disastrous consequences because it can be leveraged as a tool for massive surveillance. So essentially, this is, you see, this is the kind of the trade-off. This is the dilemma that we're facing, okay? And the other thing was they suggested us to responsibly disclose our findings to Tor project, okay? Which we have done, of course, right? And so let me also share some of the reactions from the Tor team. And I'm going to anonymize also their names for obvious reasons. So I'm going to show, because I think it's kind of funny, but then we received a lot of interesting feedback, okay? So this is several different people. These are different people. And the one that right now that I like the most, like the most funny one is that one right there. It says, I'm happy to hear that reviewers shut down the paper. So it was not very pleasing to hear this. And then we have more constructive feedback, okay? Mentioning issues involving legal concerns, touching on these points of worrying about massive surveillance, all these points, okay? And so essentially they're hinting at the fact that our research at that moment, we're basically suggesting an attack to Tor. And I mean, Tor is also their baby, I understand that. So they were also, it's normal that this causes some uncomfort, okay? And so they expressed it, which is nice. I think it's super useful. And then we've also gotten some suggestions in terms of what to do next, okay? And they were also very constructive, both in terms of the reviewers that sent us some comments in the end, and also the Tor project team, which and they were super helpful. We received tons of comments, so this was really awesome. And so ultimately, what we were recommended to do was to go slowly and essentially start looking at the problem, framing it as an attack to Tor, because there has been a lot of research in Tor, right? Tons of attacks have been published, but ultimately the goal is not to shut down Tor, is not to tear Tor down, let's say, but it is to help identify vulnerabilities and to make it stronger. So ultimately, okay, and so that's the ultimate goal. And so they suggested us to do that, and they also suggested us also to think of potential countermeasures. Okay, again, this would force us to do one step back. Okay, and of course, this was also kind of enlightening because we just jumped into the problem right away without thinking of all these implications. It was a learning experience. And so this is what we've done. Okay, so what we've done, and this is what I'd like to share with you for the rest of the talk. And in the first part, I'm going to tell you our first steps, or our main steps after that first submission, what we've done in order to kind of study Tor from the perspective of an anonymity system that aims to provide some guarantees, some security properties, some security assurances, but it's maybe vulnerable to some attacks. Okay, and we want to study whether or not the system is vulnerable to such attacks, and in particular, we want to study certain kinds of attacks, and then you'll see why those attacks that I'm going to present are interesting. Okay, and so in the first part, this is what we've done. We've recently published this work. It was presented this year at NDSS, and I'm going to spend some time just giving to you an overview of what we've done. And then I'm going to save the last minutes of this talk talking about the second point, which I still think it's important. Okay, I think there's a real dilemma going on here in terms of there's a conflict here between security and privacy. Where we should draw the line, and I still think there's space to do other things in terms of improving the ability of law enforcement to make things or investigations more easy to track, to investigate under certain restrictions. Okay, and it's exactly this dilemma that I'd like to explore in my future research, and I'd like to share some thoughts with you. Okay, good. Feel free to interrupt me if you have any questions or if something is not clear. Okay, especially because now I'm going to get a little bit technical. I try to make things understandable, very high level, but just raise your arm in case you have any questions. All right, so the first part is I'm going to present you this attack, this technique, and this is a technique that will allow a potential attacker to de-anonymize specific flows. Let me just switch this. Maybe just HDMI, is it enough?
No, I don't think that. Maybe. Give me a second.
Oops. Okay, cool. Let me also keep track of my time. Okay, so part one, I'm going to present you a new attack which aims to kind of identify some new vulnerability or kind of demonstrate that certain already theoretically known vulnerabilities can be exploited in practice. And I'm going to show how our attack works for this particular kind of traffic, Tor onion services. And so I'm going to go slowly explain what Tor is, first of all, and then what onion services are, so that you better understand what are the challenges involved and why is this interesting, okay? All right, so in general, internet users, they are at odds with a lot of with pervasive tracking and online surveillance. In other words, there are certain users, they have the need for kind of anonymity, online anonymity. Think of journalists, think of activists, whistleblowers, etc. Okay, and what we have in the internet today is that you don't have by default, you don't have anonymity, because communication involves sharing both the sender and the destination's IP addresses. So think of Alice accessing a website, and Alice opens the browser, establishes a TCP/IP connection, and all the packets exchanged carry in the header the IP address of the sender and the receiver. Okay, which means that the receiver can tell who the sender is. The sender can tell, or the client can tell who the receiver or the destination is, and anyone intercepting the flows, the packets traveling through the internet, can also tell who are the communication parties. Okay, so this is what we have today. And this motivated the development of privacy-enhancing technologies like Tor. Okay, so in Tor, what they try to do is to make things more complicated in terms of identifying the identity or the IP address of the client, okay? And so the way this works is that Tor basically consists of a large network of relays of nodes. These nodes are contributed by voluntary people, okay? And they participate in a common protocol, okay? So what clients using Tor do is that they download a piece of software from the Tor project. This can be also a browser, Tor browser, and then they can just launch the browser and start browsing the internet while concealing their own IP address. So Alice can do that, concealing the IP address. So how does this work? What happens under the hood is that Tor, what it does, it relays the communication through multiple nodes, okay? These nodes usually are 3 nodes. They have given a name. Usually they are named the guard node, the middle node, and exit node. This communication is encrypted, and it's encrypted using multiple layers of encryption called onion routing, okay? So that Alice encrypts the packets. When the packets, as each packet travels through one node, each node peels one level of encryption and passes it over to the next one. Okay, so that each of these relays only knows the immediately after and immediately before relay. So no one alone can tell the entire source and destination of communication. Okay, and likewise, the receiver cannot tell who the real sender is because the IP address that the destination sees is the IP address of the exit node. Okay, so this is the basic mechanism. And this mechanism is called circuit, okay, which is basically a tunnel through which you can send TCP connections, okay, arbitrarily. Now, the other nice thing that Tor has is also the ability to establish, to protect the communication or the anonymity of the server itself, okay, which is even more interesting, okay, because now we have to guarantee that the client must be able to contact some service on the internet, right, without revealing the real IP address of that service, which is kind of a challenge, okay? And the way Tor solves this, or the Tor developer solve this, is by creating something quite interesting called onion services. So basically, onion services is a technology mounted on top of Tor that uses this basic primitive of circuits, so that we can have one server that can decide with the client to communicate, to establish 2 circuits that meet each other at one particular node called rendezvous point, okay? And given that each circuit just hides the IP address of the client, since both of them are connected to the same rendezvous point, nobody in any end of the communication knows the real IP address of the other, okay? And so this is called, then what we see here is a session, a Tor onion service session, which if we now look closely, have not only 3 relays, but it has 6 relays in the communication for this particular reason, okay? But now there's the question, so, but if I don't know the IP address, how can the client know how to locate a particular onion service, okay? And so to solve this problem, what Tor does, it has its own domain name system, okay, where these services can be given names, something like xyz.onion, which then translates to a public key, and there's an entire complex protocol going behind it. And the system itself has a way to resolve this name so that both the Alice and the server, they meet at this rendezvous point securely, okay? And once this connection is established, Alice doesn't know the IP address of the service, okay? So this is, I mean, basic, and this is the basic mechanisms that make Tor work and provide both the client side and server side anonymity properties, okay? This makes sense so far? Yes? Okay, cool. Now the question, the more interesting question is this safe? Is this 100% secure? Okay, can the system be de-anonymized somehow? Okay. And so there have been a lot of approaches to try to break the system. The one that I'm going to explore here in more detail is one where we take advantage of information that these protocols still leak when information is being transferred over the internet, okay? So imagine now that we're basically, we have Alice. Alice is contacting this service, WebMed, and what we have here is a basic Tor circuit, okay? Alice opens a browser, establishes a Tor circuit, and all the communication is going to be tunneled through that circuit, okay? So imagine now that we have an adversary there, and the adversary can intercept the communication between Alice and the guard node. Okay, keep in mind that all these guard nodes and the relays are publicly available. I mean, are publicly known because they have to be kind of known by the clients so that they can establish a route in the network. And so suppose that we have an adversary in position to intercept those packets right there. And what can he learn? Okay, he cannot learn the contents of the payloads because the payloads are encrypted, as I mentioned before. Okay, but there's already some information available in the headers, right? The IP addresses of Alice's machine and guard relays. But most importantly, it's also possible to observe certain interesting properties of the traffic itself. Okay, you can see when packets are sent. When packets are sent, you can you can determine what's the size of the packets. You can determine what's the interpacket timings. Okay, and that reveals a lot of information. Okay, suppose that Alice is streaming a video from that website. Okay, so you are going to see consistently a stream of packets changing lengths and changing certain times, and that pattern is going to be different if we are just downloading a static website, static web page. You see, so that already reveals a lot of information. Okay, and so based on this information, what people have trying to study is to what extent this information can be leveraged to de-anonymize Tor itself. Okay, how precise we can go in terms of using this information to, in terms of being able to determine what websites Alice is accessing in this particular case. Okay. And so I'm going to tell you about two different and two complementary approaches that people have studied over the years. One of these techniques is called fingerprinting. Okay, fingerprinting. So what's the idea of fingerprinting? So in fingerprinting, the idea is that the attacker starts by building a database fingerprinting. Sorry, a fingerprint database. Okay, a fingerprint database. So what is this? What is this? So basically, a fingerprint is a sort of a profile of the typical access patterns that one observes when visits a particular website. Okay, so suppose that I visit like CNN.com, or if I visit X.com, or if I visit Facebook, the sites, they have different characteristics every time that I visit. So what attackers can do is basically you perform multiple accesses to a particular website, you derive statistical information, and then you name that as a fingerprint, and you save that fingerprint on a database, and you associate that fingerprint with an IP address, right? So you know, okay, if I observe this fingerprint, then it means that it comes from this website with certain probability, right? And so what an attacker can do is basically you can create these fingerprints by just screening multiple different websites. Okay, so you go to WebMed and you go to Swiss Medical Network, and then you go to Swiss Vision and so forth. And so you start basically visiting a large number of websites. You build this database, and then once you have this database, then it's the time when you can start matching fingerprints while trying to analyze what certain subject is accessing. So in this particular case, we have Alice that's trying to access a website. So what we do is the attacker just observes these patterns, calculates this fingerprint, and then tests, you see, how close the fingerprint that we collected live matches the fingerprint or a fingerprint in our database, okay? And if we have a match, then the likelihood that Alice is accessing that particular website is high, okay? Now, what happens if we don't have a fingerprint, if we don't have that profile or that fingerprint in our database, then we don't know, right? So we don't know, there are certain limitations in this. Now, the other approach, and this is the approach that, that we're gonna be more focused on, is flow correlation, okay? So in flow correlation, the idea is that we're not just looking into the client side, but our idea is to see, or the idea of the attacker is to see whether it is possible to sort of correlate the characteristics of flows as they enter the guard node and leave the exit node, okay? So what we're seeing here is basically a larger kind of representation of multiple clients. In this case, we have 3 different users accessing two different websites. 2 of them, they access webmed.com, and then the other one accesses the x.com website, okay? And so there we see some sort of the representations of the kind of fingerprints that we are observing at the guard nodes, but we also see the representations that we see close to the exit nodes, okay? And so if by just looking at the drawings, well, which one do you think you'd guess belongs to whom? Can you give it a try? Who's accessing which? Maybe the colors are not perfect, so I'm going to help. So now imagine, right? Imagine that we have a powerful attacker, and our powerful attacker is able to intercept the traffic at multiple ISPs, you see? And so what it does, it basically, the attacker collects all this information, okay? Collects this information, collects this data, and then runs a correlator, okay? This can be like a centralized place or distributed, doesn't matter. It's basically a function that tries to match one with the other, okay? And so depending on how good this classifier is, this algorithm is at performing this classification, then here we can have like a match, okay? And so the idea here is that if you look closely, basically the patterns that the attacker can observe at the exit nodes, they resemble or they have very similar characteristics to the patterns observed at Alice and Charlie, you see? And so by that, you can gain very high confidence that both flows are correlated. And so you can de-anonymize end-to-end, right? Know that Alice IP address is accessing the servers with that particular server with that particular IP address. So you see the idea? So now if you look at this from a global perspective, what happens in practice is that these ISPs can be spreading all over the world, right? So you can have different ISPs, okay, different entities like intercepting this traffic. And so they can, in theory, start like sharing this information and performing this kind of operations jointly, okay? And so this is what Tor Tor is not designed to sustain this kind of attacks, okay? But then is the point where these attacks are becoming more practical, okay? Good, so we have these 2 approaches, and these 2 approaches, researchers, they have started investigating these 2 techniques for Tor circuits, okay? And remember that Tor circuits, they only protect the anonymity of the client, okay? The server is still visible, is still identifiable, okay? What if we now try to do the same thing for onion services, right? For onion service sessions, is it possible to apply these techniques if we focus on that particular kind of traffic, okay? If we are concerned about, evaluating the how strong Tor can be in terms of providing security from, in terms of protecting anonymity of the server, how well can these techniques go in terms of being, threatening to that kind of traffic? So on the one hand, on the left-hand side, we have website fingerprinting, and people have demonstrated that it is also possible to apply fingerprinting for Tor onion services at the client side, okay? But it has a downside. It requires building this database, which is a little bit more tricky because these onion services, they change quite often. So it's quite difficult to maintain these databases. And furthermore, there's a limitation, which is you cannot tell what the IP address of the destination, okay? Because the IP address of the destination is still hidden behind that circuit that connects the rendezvous point, okay? So you still don't have access to that information. Now let's move on to flow correlation. So in flow correlation, this technique is more appealing, right? To de-anonymize Tor onion service sessions, because it has the potential to also reveal the IP address of the client and the server side, okay, which constitutes the real attack, right, to this kind of traffic, okay? But, and this is the point where we are entering into our research contribution, but the problem is that doing this kind of analysis for onion service traffic, it's very hard, okay? It's pretty hard, okay? And now I'm going to show you why is it hard and what was the main idea, the main insights of our approach to solving this problem, okay? Okay, so if we try, so the basic approach would be, okay, let's take the state-of-the-art flow correlation technique that is currently applied to Tor circuits, and let's see how well it works in Tor onion services, okay? And it was precisely what we've done. So the state-of-the-art technique is a system called Deep Coffee. It was presented a couple of years ago at SNP. And it basically, this is the state of the art, which basically relies on training a deep neural network, okay, with many flow samples from flows, okay, from the client side, the server side. The researchers, they build a large database. They have to simulate, they have to run in a controlled environment, a large number of experiments to generate these flows, and then they use that data to train this DNN, okay? And so once you build that model, after that point, you can just apply it as a classifier, okay? So here we see that then the attacker only needs to collect, intercept traffic at the client side, then at the exit node, and then you run this classifier, and the classifier, what it does, it gives you a score. The system gives you like a threshold by which it says, okay, this is correlated or it's not correlated, and based on that, you have like an accuracy score, okay? Now, something that's interesting here is that to train this particular classifier, we are in the case where the traffic that Alice sends to the guard node is tunneled via Tor, okay? So it's basically modulated in certain so-called fixed size cells called Tor cells. And so all the payload is going enclosed and modulated inside those cells. At the exit node, it's already in the open, okay? Because all the layers of encryption were removed, okay? And so at the exit node, the access to the server is, regular HTTP or HTTPS, okay? So the traffic is going to be, very different from what we see in the beginning, okay? And this gives a lot of information to this classifier. Now, if we apply this to try to de-anonymize Tor onion services end-to-end, we have some challenges involved here, because now we no longer have this setup of 3 nodes, but we have how many nodes? Remember? 6. We have 6 nodes, exactly. We have 6 nodes, and basically these 6 nodes, they are connected via 2 circuits that meet on that particular rendezvous point, okay? And this will introduce some complications. Complication number 1 is that now near the guard node, okay, that connects the onion service, that traffic is also modulated because the onion service connects to the guard node. And so you cannot, the patterns that you would see typical of the unmodified accesses to the server side are no longer manifested, okay, because they have been manipulated. They're different, and this will hurt the classifier. Okay, this is first difficulty. But now there's another difficulty. If we think about this a little bit more closely, now the server hidden behind an onion service, it also connects to a guard node, okay? Which means that both the clients and both the servers, they connect to guard nodes. So there's no longer an asymmetry in the connections, you see? So when we are collecting data of a client that connects to a guard node, you no longer know if that flow belongs to a client or to a server, you see? Which introduces a complication, which if you no longer can distinguish clients from servers, all of a sudden you can start combining client flows and with server side flows, which are not going to yield any benefit. And this only introduces degradation in performance. Now, there's additional complications because the problem is that now the server can also use the same flow to multiplex connections that come from multiple clients, okay? So all of a sudden, you have a distortion at the side of the exit node that results from the combination of multiple clients accessing at the same time, okay? So you have a degradation in terms of you have information loss at that time, okay? And finally, we've also observed that deep learning classifiers, they become very heavyweight in terms of performance. So now imagine that an attacker needs to perform a lot of different combinations. This will slow down the performance a lot, okay? And so our research question here was basically to try to improve the state of the art in regards to developing a more accurate and efficient flow correlator classifier for onion services. So this is our goal. So can we actually build a system that can give good results, okay, in terms of enabling end-to-end de-anonymization of onion service sessions? And so the answer is actually yes. This was a project that took us. It was quite challenging, and I also can tell you why it was. I mean, it was challenging for many reasons, but there were a couple of them that I can also share with you. And the attack, we gave it the name of sumo attack. This is pun intended with that guy right there. But sumo attack comes from an algorithm that we use as the central algorithm for correlating the flows. Okay, and this is what we call sliding subset sum, which is basically we draw this idea from the classical subset sum algorithm that we basically use to correlate flows very efficient, so that we don't need to have like a heavyweight deep learning classifier performing the correlation. Okay. And then our technique not only allows for performing this flow correlation attacks on onion service sessions, but it relies not only just on a central classifier stage, but it's actually a pipeline of classifiers. Okay, and the idea why? Because the idea is we want to perform multiple stages of analysis before we finally correlate flows that we believe that belong between clients and servers. So we want to run multiple stages where we remove flows that we believe are not relevant for our classification. Okay, and so we've built this system. We implemented the prototype, and we evaluated on a large collected data set. And this was bulk of the work because we have really to do a lot of experimentation. We did experimentation to collect traffic, generate and collect traffic like this, then to train our other models that we use, and I'll show in a second, and then also to verify and validate against other systems and so forth. So there's a lot of experimental work going on. So in a second, I'll explain how it works. I'll give you a glimpse on our approach, how the system works. Before that, I'd like also to thank my team, because this was, I mean, especially my students, This was joint work with other people, people from other groups, from CMU, from University of Waterloo, and then from Portugal, also from University of Porto and Faculdade de Ciências of Lisbon. So this was really teamwork, and compliments to our students who, burned a lot of cells, brain cells in the process. So what's the idea? So how does the attack work? So as I was mentioning before, our attack basically consists or is implemented by a pipeline that has multiple stages. And in particular, we divide the processing of flows in two phases. One phase that can be processed directly by the ISPs, and then we have another stage or another phase that is performed by the correlator. Okay. Ultimately, the end goal is, you can imagine that what enters at the left-hand side is basically the samples that ISPs collect. They get into this pipeline, and then in the end, the system will try to match them and then again produce a result and say, okay, these two flows are correlated and the IP addresses are these or not these. Okay. And so I'm going to briefly go through each of these phases. So in the filtering phase is the phase where essentially we collect the flows from ISPs. And this is one of the stages where we observe a lot of more noise, because it's the time where you don't know if a flow belongs to the client. It's a time where you don't know if that flow is accessing a particular a service on the open web, or if you're accessing an onion service. So there's a lot of noise. So what we do is we perform multiple stages. What we see there, source separation and target separation, which are basically ML, machine learning classifiers that we've designed specifically to remove and say, okay, this is basically belongs to the client side or to the server side, you see? And so the flows just get into this pipeline. We are removing those that are not considered relevant, and then we selected those. And so in the end, we just come up with like hopefully clean samples of flows that belong to clients and belong to web services, okay? To onion services, sorry, not web services. Okay, once we have these pairs, then we move on to the matching phase. And then in the matching phase is the time where we're going to take as input the flows of clients, the flows of onion services, and then we try to come up with a decision, okay? Now, one of the tricks that we've developed here is that we are not going to use deep learning for this task because we want it to be really efficient in scale. And so we're going to use this stage right there, the algorithm based on subset sum. So I don't have time to explain all the details, but this is just to give you an idea of the idea. But the other insight that we also use that other people haven't used so far is the ability to also use information from absolute times. So people have not used the information regarding the absolute time of when packets arrive at both endpoints. And we do that, okay, which we've seen that we can leverage it to yield very good results. Why? Because you can just overlap flows one next to the other. Okay, it flows from the clients, it flows from the server side, and then you can put them one very close to the other, and then see that they have to be very close to the other. So clients send packets arrive at the server side. And so the volume that you expect in both endpoints have to be very close to one another, okay? And so this is how we do it. So we start by just getting the flows as input. We match them together. Then we create buckets, okay? And then we apply a series of one algorithm that we call the sliding subset sum, which is basically going for each window, goes window after window, and check the similarity of the volume that arrives from client and that arrives at the server side, you see? So this is more or less the intuition, okay? Good, so this is the final result. So we performed a bunch of, so to evaluate the system, we had to perform like a very, a relatively complex experimental test bed. We created, we deployed numerous, we simulated real onion services, numerous onion services, and we deployed them in various data centers across the world in different regions, geographical regions. And then we emulated real clients accessing those onion services and emulating the typical browsing behavior of clients. Okay, so and then after this, we collected a very large data set. So from this, we draw certain conclusions. So we find, first of all, that actually this works fairly well. So what we're showing here is basically the relationship between precision and recall as we basically fine-tune the threshold of classification of our system. And we've seen that it works very well for sessions of, for instance, for sessions of any duration. So suppose it already, start, comparing flows of any duration. In general, we reach precisions around 99.5% precision, which means that, in pretty much almost all the flows that are correlated by our system are correct. Okay, which is good news. And recall is also pretty high, which means that we have the ability to basically cover and detect if there is a flow, if there are flows that are correlated, we manage to kind of match them at a very high rate. So we also check that other aspects related to efficiency. So we've seen that we also measured the time to train the system, which is really fast. Then, so because in the case of our pipeline, we have the early stages, which also need some training, but it's relatively fast to train, and the correlation is also very efficient, especially at the correlation stage, where we can outperform the state of the art by 2 orders of magnitude, which is, I think, also good news. Now, getting close to the end of in this part. We've also seen, yes.
This system, the show works. If you go 2 slides back.
Yes. One back, yes.
Input and every output. How does the system work if the number goes down?
If the number of what? Yes. So I don't have the numbers here, but we have the numbers in the paper. So we've done precisely that analysis where we reduced the number of flows that how complete is the view of the attacker. Okay, and you see degradation, but it still fares pretty well. Okay, I don't have the numbers here, but then I can take a look at the paper and then share that with you. Okay. Good. So we also did one. We had this question which was, okay, good. So you have a classifier. We have a technique that can work very well. That can work well. But now the question is how realistic is this threat in terms of Tor? Because you need to have vantage points, right? You need to have multiple ISPs that need to join forces, like collect the traffic, and then run this algorithm, right? And so we did a study which basically consisted of, we deployed clients and onion services, across the world, and we issued like 4,000, random accesses. Okay, and we computed what's the probability of both guard nodes of the same session to be in the same country, for instance. Okay, and this is what we've seen there. So we've seen that the Tor network the guard nodes are highly skewed towards certain countries, which means that we found, for instance, that in Germany, like 10% of the cases, or 10% of all the circuits that we've generated ended up in Germany. Which means that if the German kind of government decided, okay, let's just, start analyzing this kind of traffic, 10% of the connections that we've done, of course, this is probably not representative of everything in the world, could be analyzed, which is not small, right? And then we did another analysis of, okay, so what happens if multiple countries start colluding and joining forces, okay? And this is what we have on the right side. Okay, so as the number of colluding countries increases, then of course, as it would be expected, our coverage or the coverage of the attacker increases. Okay, but what's surprising is that we only need a relatively small number of countries to collude so that we can still kind of, that we can cover a large fraction of traffic, which is kind of surprising, okay? Good, so in summary, so a couple of takeaways here. Traffic collusion attacks on Tor onion services are realistic via our system, our proposal, and of course the threats that they pose depend on whether or not ISPs, they can join forces and they can collude. As we were recommended to do, we're also thought of certain countermeasures, right? And because of course the system is not infallible, and there are certainly certain things that can be done in order to make our technique work less good. So one, of course, is sort of to increase the diversity, the geographical diversity of the guard nodes, okay, so that they're not just concentrated on one single country. But of course, this is hard to ensure. Things like adding concurrent traffic. This is something that we've seen, that if we do that, if you add obfuscation, it makes detection more difficult. Things like opening multiple connections at the same time, and even developing pluggable transports specialized in making traffic more leaking less information about the content. Okay, so and we also have some work on this. Okay, any questions so far? Yes.
So can you tell us what kind of collaboration you need from ISPs to monitor this? And what do you mean by colluding ISPs? Could it be just like ISPs that are not managing their traffic well? Or how do we know ISPs themselves are colluding into this?
Yes, so colluding might be a word that's too loaded with negativity. Okay, so they basically have to agree on running this protocol together. Okay, so from the ISP's perspective, what they have to do is that they have to be able to tap into their networks and then collect certain amount of traffic, certain information, certain features of the traffic, and then run our protocols. This is the only thing. Okay, from the completely kind of technical point of view, this is what you need. And then you need to have someone, which can be like ISPs collaborating with each other, or another entity that runs the correlation engine, because they have to share this information. Okay, good. So which brings us to the next, I think, sorry, I'm taking a lot of time. So, but maybe I can go very quickly over the last part, and then because there are some things that might be interesting and that will close my initial thing. So very quickly, okay, so this brings us again to our first, I think you're seeing where we're heading, right? So this brings us to our original idea, right? Of, okay, can we now kind of leverage this kind of approach to try to help like police authorities to make things a little bit easier to track in terms of criminal investigations? And so I'd like also to stress, because why I came back to this problem is because the amount of crime going on around the internet has risen a lot substantially. Okay, the market, the dark web market has grown to very concerning proportions. You have, so that's an example of one famous in these circles, the Silk Road website, which was basically a marketplace for selling all sorts of things, narcotics and other illegal products. There are huge ecosystems of payment frauds, okay, and services of crime as a service, okay, where people can hire hitmen, okay, these terrible things, human trafficking. So things are growing very, very, very concerning, okay? And also other researchers are also beginning raising attention to this problem. This is a very recent study from published in Nature Scientific Reports just a couple of months back, where they studied, like they basically studied the onion services available on via Tor, and they found like a lot of content, hundreds of thousands of onion service domains, and they found that 1/5 of all of that was just being dedicated to child sexual abuse material. So this is really heavy stuff. And so what I'm not saying that all of this support, technical support, is provided by Tor, so it's not limited to that. But what we can see is that the anonymity networks, and Tor in particular, are one of the vehicles today, especially onion services, that enable service providers and consumers and producers of this kind of content and services to protect their identities on the internet. Okay, so most of dark web services that we see today are backed by onion services, and Silk Road is one of the, it was one of the most kind of one of the first services to be actually tracked down by FBI, and then FBI and Europol. So there's been investigations around this. So what we essentially like to help is raise this question of whether or not we can help law enforcement authorities to help de-anonymize this traffic at the network level, always from the perspective of offering this service in a responsible way. Okay, and so the research proposal that we're basically kind of investigating and analyzing and pondering is to build something that for now we're calling federated traffic correlation. Federated in the sense that the idea is to have ISPs and law enforcement agencies to collaborate into offering a service that will allow law enforcement authorities to de-anonymize certain communications based on certain queries. Okay, so we see kind of an example of something that we envision. Okay, you are in the context of a criminal investigation, and inspectors, they need to investigate particular communications. And so you can imagine the system offering some sort of interface that will allow the operator to issue these queries and keep track of source and destination of communications. So now the idea is how, or the challenge here is how you build such a system in a way that it it protects. So there's multiple challenges. I'm going to briefly go through each of these ones. So the first one has to do precisely with the issue of preventing abuse. How can we prevent governments from abusing, right, or ISPs from abusing this service to monitor people and then to sell that information to others? Then the other problem of ISPs. So ISPs, to perform correlation, they need to share metadata, which is also sensitive stuff. And it goes against things like GDPR compliance. So it's very sensitive. Then in the third point, there's the systems related challenges, which is things that involve how do you process all this amount of traffic at scale? How do you process those queries at ISPs? And then finally, how do you improve the classifiers, because there's a lot of traffic going. So there's a lot of room still to improve our ability to correlate flows and also to expand to other kinds of networks beyond Tor. Okay, so we have a bunch of ideas to tackle each of these issues. In the first point, our idea is to realize that we actually are not sure that it's that easy or that that compelling for different countries just to join forces and all of a sudden start monitoring the entire traffic all over the world. So that would be typical of a totalitarian global state. In practice, there are going to be national security issues that will prevent countries and law enforcement agencies from fully collaborating. So, and the same thing applies to ISPs. Okay, there are security reasons, there are competition reasons between ISPs, so they are very fond of protecting their infrastructure, and I think that that can play in our favor. And so then, based on that, our idea is to sort of develop systems that can, on the one hand, ensure that only if you have a quorum of authorized entities, then queries can be processed. And then we also are thinking of using things like smart contracts to ensure that all the parties, perform as expected from all the steps of the protocols. And if you have questions, I can also elaborate a little bit on that. So to the others, the idea is also to explore ways for enabling privacy-preserving correlation of flows using techniques like homomorphic encryption or multi-party computation. There's ways to possible paths to explore there. And then we have also ideas in other dimensions to leverage existing infrastructure in the network to speed up the handling of traffic, and then new ideas to improve our classification ability. Okay, so there are many conclusions. I'm sorry that I slipped up a little bit in the talk.